panel, and he's talking about asymmetric approach to gravitational scattering and all that.
And I haven't changed the title of my talk. And by the way, sorry for all this affiliation. I'm trying to compete with Gia. Okay. These are past associations, present associations, and so on. So, okay, let me start with a little introduction. So this is a long enterprise, long time enterprise that started about 30 years ago, 29 to be precise. And so the idea is to take Transplanckian gravitational scattering as a thought experiment to study, in the old spirit of quantum mechanics, some fundamental issues about the merging of general relativity and quantum mechanics within a theory which is supposed to be a consistent theory of quantum gravity, like string theory. Now, and a particular problem that we wanted to address is whether and how information is preserved in a process which classically or semi-classically would lead to black hole formation and then to Hawking evaporation and so on. So this is why I decided to talk about this topic, which is very central for this conference. I forgot to thank the organizers and, of course, the Studium for this kind invitation. So the game, as I said, started about 30 years ago, where in a single week, I think, there were 3 or 4 preprints about Transplanckian gravitational scattering. In particular, 2 of them dealt with strings, but in different regimes. One was by Amati Ciafaloni and myself, hereafter ACV, and then there was parallel work by Gross, Mende, and later Oguri. We took a rather different route, but at the end of the day, in a kinematical region where both approaches can be justified, we found essentially perfect agreement between the 2 methods. Unfortunately, I have no time to explain that. Much later, I got interested with this group of Italians dislocated in different countries about the scattering of closed strings of a stack of branes, a somewhat simpler problem, because you have to appreciate the fact that in a particle-particle or string-string collision, the metric is a priori unknown. Okay, you have to, even classically, the problem is very highly non-trivial. Whereas if you have a big stack of heavy branes, the geometry is essentially determined by the brane system. So, but for lack of time, only the first process will be discussed here. So this is the outline, but of course I don't think I will, I'm sure I will not be able to cover all these topics, and so most of this will be just a quick reminder of some results. What I wanted to concentrate upon today is really this last issue, some kind of energy crisis that we found, how we solved it, and so on. But okay, I want to set up the framework. So roughly speaking, I hope to spend some 40 minutes covering the rest, and then to devote at least the last 15 minutes to this more recent work. But okay, I would like at least to mention these different regimes that we have studied that we call weak gravity, quantum field theory regime, weak gravity still, but quantum string theory regime. In the first, the stress will be, the emphasis will be on recovering elastic unitarity. In the second case, we will be able to show that unitarity is still exactly satisfied, but in a in a multi-channel setup, so it's inelastic unitarity. There is then a string gravity regime in which at least we can argue, at least approximately or in a rough way, to also have unitarity under control. But finally, we will enter the regime of strong gravity, which eventually leads to the regime of collapse, where progress has not been as as good as in the others. So let me go quickly through the easy part, and then I'll tell you, what we were able to do on the more difficult part. Oh, I will also finish with a comment on this paper, whose author is in the audience, Gia, but I don't know if I have time for it, honestly. Let's start with the parameter space for collision of two strings, say two light strings at ultra-Planckian energies. And we need ultra-Planckian energies if we want to have any hope to form a black hole which is semi-classical, of course. So the length scales, we work in impact parameter space, okay? And the reason is that, well, first of all, we can do our calculation in a much better way, but also working in impact parameter, it makes a closer connection with a classical problem in which you do have a collision at different impact parameters. So one length scale will be the impact parameter of the collision. The other scale is the gravitational radius associated with the center of mass energy. Now, if you are, so these are classical parameters. If you are in classical GR, these are the only two scales in the problem, and everything will depend on the ratio of these two scales. And you don't even have to go to ultra-Planckian energies. I mean, things are invariant and the rescaling of everything. But if you are in a quantum theory, you also have a Planck length. And if you are in string theory, you also have a string length. And I remind you of the well-known relation, at least at weak coupling, between the Planck and the string length. We will be working all the time at very small string coupling so that the string length is parametrically much smaller than the string length. And this is what allows us to neglect effects which are really proportional to the Planck length. But we don't want to neglect the string length. So we have really three essential parameters, so two ratios, two-dimensionless ratios, and this is why our phase space for the process is a plane. And the important thing is that by playing with energy and with string coupling, we can make the ratio of Schwarzschild over string length arbitrary, okay? Bigger than 1, smaller than 1. We can play with these parameters still. So this is why the phase diagram, the expected phase diagram looks like this, very roughly, with a critical line which at large R, large B follows a straight line, so a critical ratio for R of a B, below which you expect to have collapse, and above which you don't expect to have collapse. However, because of the string length, this straight line bends at some point and turns into this point, which means that you do not expect to find black holes whose Schwarzschild radius is smaller than the string scale. Okay, even precisely when the string scale is much larger than L Planck. So this explains the curve. Now, this diagram separates the plane in these three regions, which correspond to what I defined in the summary as weak gravity, string gravity, and strong gravity. Unfortunately, this is the most interesting, but also the most difficult region. Now, Actually, this is oversimplified. There are subregions which come from the fact that the leading order contribution to the S matrix, to the semi-classical S matrix, is a phase, which gives elastic unitarity. It's a pure phase, so with a classical action, which is real, that corresponds to this one. But if the corrections are small but contain imaginary parts, they become extremely important whenever them times the prefactor, which is very large, becomes of order 1. So this explains why you cannot simply neglect the corrections when they are small compared to 1. Okay? If they contain an I, they have to be taken. And so this complicates the phase diagram considerably, and we'll see some of this in a moment. So let's start with a weak gravity quantum field theory regime, which is how you recover unitarity through loops, elastic unitarity through loops at very large impact parameters. So if you are at very large impact parameter, your collision is very peripheral. You expect simply the particle trajectories classically to deflect each other. But if you look at 3-level scattering amplitude, you don't see that at all. In particular, in string theory, you find that the scattering amplitude at fixed angle are exponentially small. So there is very little cross sections where you exactly expect to find your trajectories to bend. Okay? Now, loops are able to correct for all that and to give really the expected physical result. So this is a typical, just schematically, the type of loop contributions that we are able actually to not only compute, but to resum, which looks a little miraculous, but you can do it if you take the appropriate limit, high energy, large impact parameters. Okay, this would be a 2-loop contribution in a closed string collision, where the red circles are the incoming and outgoing strings. The green one are the exchanged closed strings, which include a graviregion, a graviton which belongs to a Regge trajectory, and the yellow one are strings that you produce in the S channel. We'll see more of that in a moment. So after resummation at fixed energy and fixed B, you get an amplitude which looks like this. Okay? It's just the first term of the expansion I had. And you see, it becomes unitary because it's just builds up a large phase. If you start to expand this exponential, you get your loop expansion. And order by order in the loop expansion is terrible. You violate partial wave unitarity because each partial wave, these are like partial waves, exceeds the unitarity bound as long as GS goes large. So, but there is no harm to having a large phase. Actually, it's good to have a large phase because then you can do saddle point approximations. In particular, you can go back after having resummed at fixed B, you can go back to Q, which is the momentum transfer. And by a saddle point approximation, you can compute your S matrix in this region. It's obviously unitary. It's elastic. There is no inelasticity in the process. And the interesting thing is that the saddle point approximation gives you a saddle point for B, which is related to Q, so to the scattering angle, in such a way that you recover precisely, it's written here, the generalization of Einstein's deflection formula for ultra-relativistic collisions and at arbitrary d. By the way, d is the number of, capital D is the number of space-time dimensions, which for the moment I take to be arbitrary. Now, so the deflection angle is given basically by the derivative of the phase shift of this phase with respect to b. And it's correct. I mean, it gives you the expected value. Derivative with respect to E, so to the energy, give the correct Shapiro time delay of the process. Elastic unitarity is fulfilled. And, well, one last comment is that you can get to fixed, small but fixed angle at arbitrarily high energy, and yet the process is dominated by large distance physics. That's why you can do this, okay? The reason for that to happen is that the process takes place through an enormous number of graviton being exchanged, and so the large momentum transfer is shared among many, many soft exchange gravitons. So the process is intrinsically a large distance process, although there is a big momentum transfer. This is typical of gravity. Would be not the case, of course, if you have a QCD process or anything like that. Okay, so I hope this is the easiest regime. The next, yes.
The Shapiro phase shift is logarithmic in 4 dimensions.
In 4 dimensions, it is logarithmically divergent. That is. Yeah, no, but, no, we would like to go also to 4 dimensions where, as Gary is correctly pointed out, this gives a log because C sub D goes like 1 over 4 minus D. That means that there is a logarithmically, well, there is an infinite Coulomb phase in the S matrix, like there is in QED. If you go to Landau-Lifshitz, you'll find this infinite Coulomb phase. Now, for the deflection angle, what counts is the derivative with respect to B, and that is finite. So the deflection angle is the Einstein deflection. But it's true that the time delay is, so you have somehow to, I don't think it gives anything physically terrible, but it is true. There is this logarithmic infinity. You find this also in the paper by Maldacena et al. On this causality problem, that D equals 4 has to be treated separately.
Roger Penrose has written eloquently about this.
Oh.
His opinion is that this invalidates. He has some nice examples, but he makes him suspicious of perturbation around the cosmos space. His argument completely fails in
In higher dimensions, it's okay. In 4 dimensions, there are many infrared questions. In fact, we will see one of them at the end of my talk. But it's true that somehow the metric is not as asymptotically flat as in higher dimensions, and maybe one has to worry a little bit like this. If you want, the wave functions are not free. I mean, they don't go to free wave functions at infinity as fast as you'd probably like. Well, if you go to 3 dimensions, it's even worse because you get a conical singularity. So 4 is borderline. So let's accept a log for the moment and carry on. So then we can still be in the weak gravity regime, but turning on string corrections. And then we go from exact elastic to exact inelastic unitarity. And this is a nice story, which, of course, I have to shorten. So we are still in region 1, but a little lower than before. And then, you know, this picture comes back again. So what happens is that physically, the initial closed strings, through the exchange of closed strings, can be excited. Okay, so this yellow string, if this incoming string was a graviton or a dilaton, this yellow string can be anything, any excitation, okay, any possible excitation. So, and through the fact that you exchange many gravitons, you can build up a very big excitation spectrum. This, of course, is not black hole formation and so on, but it shares some properties in the sense that if you look, for instance, just at the mass, how it's called, the mass distribution of such an object, you know, d sigma dm square, d sigma by dm square, you find that this, in some region of M, increases like the degeneracy of string theory, e to the m. Then eventually turns down. So if you only looked, and it's quite universal. So you say it's not Hawking radiation, but it's a property of a final state which doesn't seem to be very much dependent on the initial state. On the other hand, we know how to write down a perfectly unitary S matrix here. So if you start with two different initial states, you will end up with two orthogonal final states. Okay, now, so this corresponds to taking those corrections into account, and you understand this as tidal excitations of your strings. You have extended objects. You have a gradient in the potential, gradient in the force. So you know actually how to compute, even by a back-of-the-envelope calculation, this tidal force. And even such a calculation gives the correct critical impact parameter at which this phenomenon kicks in. And you see it's parametrically larger than the string scale because, I insist, GS is large GS is large. It's much bigger than 1. So this we can treat very well, very nicely, and it has been done in all glory. And in the papers with Di Vecchia, Del Polonio, and Russo, where we consider a different process, as I said, scattering on branes, we still have the same phenomenon. And we studied in that paper precisely how the, how the final state is characterized in terms of the initial state, and checked all details of this unitary operator. So you, instead of having a unitary C number S matrix, you have a unitary operator e to the I times an Hermitian operator. So it's complicated. The details of how this string gets excited is very complicated, but it's perfectly unitary. Okay. Then we can go to the next regime, which is this one, in this region. You see, in this region, the string length dominates over the other length scales of the problem. So that's where you expect huge string corrections, really string. That's why we call it string gravity. And for the moment, let's neglect these corrections. We correct this correction even if B becomes smaller than R. And the reason is that the string corrections screen the so-called classical ones. Roughly speaking, I didn't have time to explain, the string corrections replace B by a B plus a position operator of the string, which has a standard uncertainty of order L string. So imagine to replace roughly B square by B square plus L string square. Of course, if R is smaller than L string, these corrections will be killed. So we feel very safe on neglecting these corrections once you are in this regime. Now, you find that the phase shift now is finite at B equals 0. Remember, my phase shift was going like B to the 4 minus D, so as a log in D equals 4, or as an inverse power of B at D larger than 4, so it's singular at B equals 0 in quantum field theory. In quantum string theory, you find that these corrections make the phase shift finite at B equals 0 with a smooth expansion in B square over L square over log. So at small b, this becomes the expansion parameter. Of course, you need a string length. This, by the way, solves the causality problem, if there is one, raised by Maldacena and company in string theory. And this is what we wrote about in this paper, still with the same Italian clan. Now,
what was the main argument for the causality problem?
For the causality problem, the main argument to recover, to have it. Well, Maldacena et al. Found that in theories which have corrections to the Einstein-Hilbert action, including R square, R cubed terms, if you compute gravitational scattering and you change the polarizations of your graviton, you can get a Shapiro time delay with a wrong sign.
But that's because of the ghost fall, right? So
Because
they consider finite number of high order.
they consider a finite number, but they took particular R square, R cube contributions which do not give ghost, as far as I understand.
Really? There are such contributions?
I don't know. Now you got me. At least which don't have higher derivatives, more than 2 time derivatives. I'm not sure if they have ghosts, honestly.
Yeah, I thought there was a tachyonic spin 2 tachyonic fall. And then spin 2 tachyonic fall contains the ghost because it's a longitudinal polarization in the ghost.
Okay. Now, okay, I don't want to enter. There have also been criticism to their saying that that there are causality violations. I know that I forgot real or somebody also wrote paper. So let's not enter into this issue because it's very tangential for me. It was an incidental remark. What is sure is that we did the calculation in string theory where there is no such a problem, and we find that that the time delays always have the good sign. So as you go towards b equals 0, nothing wrong happens. And this is very much due to this log. This log helps a lot to keep this problem under control.
Can I ask you quickly, but the time delays depend, I guess, on the polarization.
Yes, that's what they found.
What you expect.
Yeah, no, yes, that's right.
Sign is a different matter.
Yeah, the point is this. So there is a time delay due to the leading order time delay at large distances. This is given entirely by Einstein-Hilbert, has the right sign, has the conventional sign. However, the corrections can have any sign depending on the relative polarizations. And they overcome the leading term at small impact parameter. That was their point. So no matter what you do with the signs, there's always a combination of a polarization which gives the wrong quote unquote. Now, is this because they started with the sixth theory? Is this really a causality problem? They claim that they can make closed time-like curves by using this wrong time delays. But I know that there have been objections to this, and I don't have a definite opinion on this. Anyway, I wanted just to point out that the agreement with Gross, Mende, Auguri happens in this regime. In this regime, you have large strings colliding, grazing each other when the deflection angle is maximal. However, there is a maximal deflection angle above which the amplitude, the process is classically forbidden and the amplitude is exponentially depressed. Now, precisely in that regime, we find agreement between our calculation and Gross, Mende, Auguri, who start immediately from fixed angle and have at tree-level an exponential suppression, then they add loops, and finally they, after they resum their series, they end up with a result which agrees with ours. Let me skip the generalized uncertainty principle. Let's go on. What is more important for today's talk is that in string theory, even a single graviton exchange gives a complex scattering amplitude. The reason is this diagram from the old days of ST duality, that when you exchange not a graviton, but a graviregion or a stringy graviton, you get an amplitude which has an imaginary part. And the reason is that there are S-channel intermediate states, which are the same closed strings that you exchange in the T-channel. So this is the old Dolen-Schmidt duality. And now, this imaginary part is irrelevant, is exponentially irrelevant at large impact parameter, but it becomes important as soon as you go to B smaller than the string length up to a log. And like the real part, it is perfectly smooth at B equals 0. The imaginary part of this classical action with 6 in the exponent is given by this formula, which, as you see, is perfectly finite for B equals 0, but it's large. And you can go on and you can estimate the number of such strings. Now I turned my picture by 90 degrees, sorry. So the incoming string comes from downstairs, upstairs. So this, for instance, is a two-loop diagram. In the two-loop diagram, you can have as many as three intermediate closed strings. However, you have to be very careful when you apply unitarity to this loop calculation. You have cutting rules. For some of you old enough or Russian, may sound familiar, the AGK cutting rules, Abramovsky, Gribov, Cancelli cutting rules. So they tell you the relative contributions to the imaginary part due to putting on shell all three closed strings, or you see, you can cut the diagrams in some other way in which you put on shell only 2 or only 1 of these closed strings. So, and you have a counting. So when you do all this, you see how unitarity is recovered in this new inelastic context in which you have to add not only 2 excited strings, but even many, many, many produced strings. And the surprising thing, maybe it should not be surprising, but at least for me it was, at first surprising, is that the average number of strings, an average, goes, what did I say here? Well, it's basically related to this quantity, okay? Oh, okay, no, so here I took a particular case. So grows very fast with energy, grows as fast as a square of the energy. So if the number of closed strings which are produced grows with 2 powers of energy, since you have only 1 power of energy at your disposal, that means that each of them should carry an energy which decreases like 1 over E. So there is this very interesting phenomenon that as you increase the incoming energy, the outgoing particles have decreasing energy, which I called in this paper a precursor of black hole evaporation. Why a precursor? A precursor because we are in a region where you don't expect to form black holes. In fact, we find nothing particularly tricky about this regime. Simply, at some critical incoming energy, the energy of the final strings starts to decrease, reaches a maximum, which I think is m Planck, and then starts to decrease until it becomes of order m string, which is much smaller than m Planck, precisely when you reach, I don't know, do I have the diagram? When you reach this threshold. So we can explore all this region. Unfortunately, things go out of control as we try to cross this boundary. But as we come close to this boundary, the typical energy of the final closed strings approaches the Hagedorn temperature of string theory, which, I remind you, for strings of that size coincides with the Hawking temperature. So it's not yet thermal, it's nothing like Hawking radiation, but it starts to soften, and the increase of multiplicity goes like 2 powers of the energy. By the way, in any number of dimensions. So it is particularly smooth in 4 dimensions. But okay, it's not as smooth in higher dimensions. Okay, so this is this part. Okay, so far, so good, I would say, in the sense that things are more or less under control, and we get things which are either in perfect agreement with classical relativity expectations, we get string effects which seem to make sense, and all is fine. Unfortunately, the last regime, the most interesting one, where you expect classically collapse, life becomes much harder. So from now on, I limit myself to d = 4, and no string corrections are included, which could be a very important limitation of what I'm describing. So how much time? 20 minutes left? A little bit more. Okay, so this is the regime. Now, in this regime, in principle, we know what we should do. We should look at 3 diagrams which make our exchange graviton interact with each other in a non-trivial way. If you want, the leading iconal approximation is the one in which this tree diagram is the trivial tree, if you want, which is completely disconnected. So this graviton just fly all the way up. If we start to look for connected trees, we can see that each connected tree produces an effect which typically involves corrections that scale like R over B. R over B, remember, is the critical parameter for collapse or no collapse in the classical case. So we know the summing trees corresponds to solving some classical field theory, and we even know what that classical field theory should be. It was basically written down by Lipatov long ago, then we elaborated a little bit on that in '93, but it's too hard to solve. So the story is a little bit long, so I'll just give the bottom line. What we did in 9 years ago, yeah, time goes fast, with Amati and Ciafaloni, was to butcher a little bit this Lipatov theory. We froze the longitudinal degrees of freedom, if you have time and z, and only kept the transverse degrees of freedom. We also got rid of one of the polarization of the graviton, the one which was giving infrared divergences. Anyway, we butchered a lot the poor Lipatov, and then we managed to arrive at a theory where we could find solutions. In fact, the solutions were done numerically in this two-dimensional effective action by Marchesini and Onofri, and insisting on an extra axial symmetry, we could reduce even the problem to a one-dimensional field theory, which we could solve even analytically. So then what is the game was to look for real regular solutions of this effective field theory. And we discovered, to our surprise, it didn't have to be that way, that real regular solution indeed only existed for sufficiently large B over R. So there was a critical BC of order R, times a number, below which there were no such real regular solution. Now, the amazing thing was that this critical BC was in good qualitative agreement with the BC that you can get from classical collapse criteria. You have this thing of trying to construct a closed trap surface, and if you manage to construct a closed trap surface, then you are pretty sure that a black hole forms. In some cases, we could even prove a general theorem that if you could form a closed trap surface, then certainly we couldn't have a real regular solution. Anyway, so the story above B critical looked okay, but when we went below this B critical, there were no real regular solution, and we had basically a choice between real but singular, regular but complex. And and we made probably the wrong choice. We took the latter. And if you take the complex regular solution, you plug this back into the action, you get an imaginary part, because, okay, the solution is complex, so you get E2 minus something finally. So it's like a new kind of absorption, calling for some new states in which your probability goes to fulfill unitarity, and we couldn't find any obvious channel, new channel. Of course, you could say, of course, you form black holes. What do you expect? But we didn't see any sign of anything like that. So I don't know. This, I think, is still an open problem. Ciafaloni and Colferai worked a lot on this, and I think they almost came now to the conclusion that perhaps the choice of complex regular was not a good one. One should look for real singular and invoke maybe some short distance physics like string corrections, which were excluded here, to get rid of the singularity, because the singularity is at R equals 0. It's really a short distance singularity that makes this. So maybe you need really an ultraviolet completion in order to solve the problem. Or it could be much more mundane, the explanation. Namely, our approximations were really too drastic, and and we bought for ourselves the problem. So, being a little bit stuck on this, well, we turn, at least momentarily, to a simple puzzle, because we had another puzzle. And that one, I think we are, on the other hand, on the way to solve. So this is the last part of my talk. OK, so I think I'm more or less on schedule, 15 minutes, more or less. So an energy crisis. So when we did this work in 2007, we computed also bremsstrahlung, namely, because when you add these three diagrams, of course, these three diagrams mean that in the intermediate state you start to have many more particles, okay? In particular, you emit gravitons, and we managed to do a computation of the energy, the energy in gravitons per unit frequency and transverse momentum, okay? And the result was this, okay? I think the dimensions match nicely. There is a nice exponential cutoff in the transverse direction, which is controlled by B, or 1 over B. Remember, B is pretty large, so this is a nice cutoff. However, in the energy or frequency direction, the cutoff is much milder because R over B is small. We are still a small deflection angle, but okay, trying to go towards larger and larger deflection angle, though that's when you expect bremsstrahlung to take place. So the bremsstrahlung was too hard because this cutoff in omega is such that if you integrate the spectrum, well, if you integrate over transverse momentum, you just get 1 over b squared, which nicely makes this r squared over b squared. R squared over b squared is the scattering angle square, and this is very nice. However, the integral over omega is very bad, and is such that you can do it in your mind, in your head, that already at a b which is much parametrically larger than r, you already produce in gravitational waves a finite fraction of the incoming energy. So it's a very efficient, it would be very good news for our experimentalist friends to find this large. But it smelled wrong. So it looked puzzling from a GR point of view. In other words, this is too large a cutoff on omega. So we asked ourselves, what is the real cutoff that you expect in GR? Okay, in classical general relativity, if you have this process of a two-body collision. And we had there was there were plenty of gases, which I don't want now to. And we look at the literature. We also asked people around, and most of the time, people said, well, I don't remember anybody doing this, but I will give you an answer within a week, and I'm still waiting. So anyway, the best papers on the subject are by Peter Diaz, I think, and collaborators. But there were also, you see, they had this gamma factor, and there were warnings about sending gamma to infinity, okay? And a famous paper is the one by Kovacs and Thorne, where it is stressed that it's a very general treatment of the problem. But of course, they were interested in star-star collisions, star-star, and not so. But they had this limitation that the angle of gravitational deflection of stars orbit much smaller than 1 over gamma. So how do we go to ultra-relativistic or massless particle collision? There was no such a way, but okay, in the last few years, we made progress on this problem. at the purely classical level, I wrote a paper with Andrei Gruzinov at NYU. Spirin and Tomaras had similar results a little later, but in agreement. And then even more recently, we did some quantum calculation. And I will show you that we found, again, very good agreement between the two. Perfect agreement, I would say. So the calculation that I did with Gruzinov can be summarized as follows. Well, it can be summarized by giving the result, which then I will try to quickly explain. So we are still talking about dE in gravitational waves, d omega d2 theta. Now here I put theta tilde. Theta tilde is the angle, solid angle, the difference between the solid angle at which the gravitational waves comes to you with respect to the deflection angle of the two particles. Okay, if you have the two particles colliding, I told you there is a classical deflection angle. Now, with respect to that direction, we found this spectrum. So this C is like what is called in GR News functions. We get them. And you see it's a rather complicated integral, which is hard to evaluate analytically. You have to do it numerically, which is like a superposition of many waves. And in fact, we got this result by using the Huygens principle in the Fraunhofer approximation. One crucial aspect of this is the subtraction of this shock wave. You see, when you have this high energy collision of two massless particles, the deflected particles, of course, if they are massless, they still travel with the speed of light, and so do the gravitational waves that are emitted. So even numerically, this problem is very challenging. In fact, has never been solved, because it's very hard, also in numerical relativity, to disentangle the shock waves carried by the deflected particles from the real gravitational waves. Now, analytically, this is how you disentangle. Okay, you subtract the deflected shock wave. This is very much emphasized in the papers by Diaz. So I have a picture, but for once, I think the picture is less eloquent than the formula. Usually, but okay, this is to show how you can use the Huygens principle in this Fraunhofer approximation, but what you add to the optical Huygens is the time delay. Again, the time delay, the Shapiro time delay plays a role. So when you reconstruct your how is called it, large distance field, superimposing waves emitted by each point on the screen, you have to take into account that there is a time delay which depends on where you are on the screen. When you do all that and you subtract the deflected wave, you end up with a formula which I think it's amazing for such a complicated problem. Sorry, is amazingly, this was it. It's compact and simple. You can put it in the computer, and you can get everything basically. Now, in particular, it has some nice properties, this formula. dE d omega has the correct zero frequency limit that you can get from soft theorems. And it's written here. Sorry, maybe I should start with this. dE d omega is almost flat. It actually goes like log of omega r if you are in the frequency range between b to the minus 1 and r to the minus 1. Remember, we are at small r over b. However, below b to the minus 1, when you're really, really soft, then it freezes. In other words, omega should be replaced by 1 over b, and that's it. So you get a log of theta, because r over b is theta, and you recover exactly the formula that you can get from the so-called zero frequency limit, which has this log. When you go instead above r to the minus 1, the spectrum changes. It's no longer constant, d omega, but it goes like e over omega, always times a theta square. Theta square is there to tell you no deflection, no bremsstrahlung, okay? So it's over the theta square. That's nice. That's unlike what we got in the old calculation. And then, unfortunately, a spectrum which goes like d omega over omega, you cannot integrate it over omega to infinity. You get a logarithmic divergence. And we have somehow to cut off this integral. Now, there is a frequency at which two things happen. Our approximations break down. And the Dyson bound that Gary mentioned, d over dt less than 1 over g, gets saturated in the sense that, okay, if you Fourier transform and you go back from frequency to time, you find that if you insist on this 1 over omega up to omega equal infinity, then you get, at short times, you get a very too much power, and you start to exceed this bound. So if you cut off your spectrum there, you also get the total efficiency. And now you see it's a perfectly nice, finite, small result. The efficiency goes like theta squared. Okay, now the end of the story, which I will do very quickly, is that we did the quantum calculation a little bit later, which also carries some interesting points. So trying to improve on this earlier work. So there are a few observations which I think are interesting. One is that the soft graviton recipe, there are these famous soft theorems on gravitons and on photons, for instance, which tell you that, okay, in the zero frequency limit, you only need to attach your external particle, your final particle to the external legs, okay? You get the singularities. But these have to be amended a little bit because in our process, the internal exchange gravitons, these Coulomb gravitons, are also very close to their mass shell. So, because of that, sometimes the emission from the internal exchange gravitons is as important, if not more important, than the emission from the external legs. Okay, this complicates matter, but it's important if you want to calculate the energy loss, because this is typically carried by the not so soft gravitons. Okay, they are much softer than the initial particles, but they are not extremely soft. And the other thing, which is even more important, is that when we go above r to the minus 1, there is a change in the spectrum because now, well, classically we saw it already. Quantum mechanically comes as a decoherence effect. It's basically the fact that you have these bending trajectories, and if you emit a graviton at some rung in the ladder and is reabsorbed at some other rung on the ladder, you find that there is a lack of coherence, or there is a suppression if omega is much bigger than r to the minus 1. This is explained a little bit here, but okay, you have to read the paper, I guess, to really see how it works. But this decoherence is what in this quantum calculation causes the break at omega equal r to the minus 1. So what we find very amusing is that the emergence of this scale, okay? You have this problem with these very energetic initial particles. You look at the spectrum of your final gravitons, and you find that there is this characteristic energy scale which is given by 1 over r, okay? Which is, you know, the Hawking scale. Now, okay, if we take this into account, we get something which looks like the classical result, but not quite. I mean, if you were still awake, you may remember in the previous transparency there was this function phi, which appeared in the classical calculation, but it appeared in an exponent, whereas here it doesn't appear in the exponent. Anyway, to make the long story short, we have still to take account, when we took also in account something else, that there is an aconal phase associated with the 3-particle final state as compared to the 2-particle final state. So we corrected also for that. Then we get exactly the classical result if we send h bar omega over E to 0. Anyway, so now we have this calculation done in 2 different ways, 2 completely different ways, because in one way we use Huygens principle, in these other ways we sum diagrams, computed cross sections, and so on. We talk about gravitons here. There we talk only about gravitational waves. So, I mean, it's very reassuring that in the end we get really the same result. So the last few transparencies are about some slides, which I actually physical review. Well, what did they do? They reprinted them. They liked them. I don't know how. Anyway, so this, for instance, is a d sigma, d omega. It's integrated over azimuthal angle, so it's the differential, not cross section, distribution of energy per unit frequency and per unit azimuthal angle, no azimuthal, polar angle. And you see here this plateau, and the length of this plateau is logarithmic, and this is what gives the logarithmic dependence of the plateau. But if you go to omega bigger than 1 over r, which means log of omega r bigger than 0, then you run out of plateau, and then you go down. Now, this drop of the distribution is due to phase space, to the fact that there are no collinear singularities, so the real collinear in the direction is depressed, and this is the cutoff in Q in momentum, in transverse momentum. So anyway, you find, well, and we could also draw some nice picture about really the both the theta and phi distributions, or theta x and theta y of this solid angle distribution at different value of omega r. So we really know everything about this bremsstrahlung. The only thing that remains is really this large frequency cutoff. And also, we have some ideas, but we haven't done it yet, of how to go to large theta scattering. So we want to go forward and approach really the collapse region. So, but if that kind of behavior persists at as we approach B of order r, then the gravitational wave or graviton distribution becomes more and more isotropic. And again, we'll find that the average number of gravitons will go like the entropy of a black hole, Gs over h. And again, the characteristic energy of each one of them will be of the order of the Hawking temperature. If we are not yet at B of order r, we find a difference, namely the transverse momenta are cut off by 1 over b, and the longitudinal ones are cut off by 1 over r. So the shape of the distribution is cigar-like, okay? Small transverse and bigger longitudinal. But as we go to b equal r, they will all become avoided 1 over r. So this is basically the end. I think this maybe I can answer in the question session, if there is one. Thank you very much. Yeah, I over.
Any questions? It's okay. Comments?
So this large theta you mentioned, large theta.
Yeah, large theta, we have not done yet, how to go to large scattering angle. Well, this would be very interesting to bridge the gap between us and, for instance, what you did, because we are still fighting, as I said, the large theta problem or the collapse region, it's hard. So for the moment, we stepped back. We went back to small theta by trying to understand what happened to the graviton radiation. Now, well, the problem will be how to go on from there. Since we have a recipe on how to include bremsstrahlung, we hope that this same recipe may work at higher order in theta. In that case, we have a guess on how to implement this thing at all theta. But okay, we are still working on that. So this is about you. Can I spend, if there are no questions, I can spend 1 minute on this?
Yeah, I think if maybe it's
If there is no other question, because I mean, I should give priority to. So, I'm giving his talk now. So they proposed this interesting exercise. If you want, study the process 2 to n. So you have 2 ultra high energy gravitons going into n ultra low energy, I call it, gravitons. And I think the claim, please correct me, is that the most important contribution to unitarity, okay, this process should be unitary in a unitary theory, so if you sum over all final state, you should get probability 1, comes from a value of n, which is roughly of the order of the black hole energy, the black hole entropy for energy E. But, okay, what we found somewhat surprising is that this statement, they seem to reach this conclusion by working at 3 level. Namely, they compute this 2 to n, which is a formidable task already, I must say, to compute this object at high energy for very large n. Now, I think if it's true, it's quite amazing. Now, I have only one slide to say where my reservations are, but I would like to, maybe in the discussion, we can go to that. Now, the problem is that typically, at least from our own experience, exclusive cross-sections have infrared singularities. So, you know, in ordinary field theory, if you take a 3-level cross-section for fixed n, you find infinity simply because when you integrate over the phase space of the final particles, you have the soft region, and if the theory has massless particles, typically this leads to infinities. Now, if instead you fix the final momenta or the final particles, and you include all virtual corrections, so loops, not final particles, but loops, then they vanish. All the exclusive cross-sections vanish. And it's only if you define inclusive enough cross-sections that you are free from infrared problems, and you can compute what are called typically infrared insensitive quantities. So we are working on this. Okay? This is ongoing work with Massimo Bianchi and a student of his. And we think now we can reinterpret your result in terms of inclusive enough objects, and to justify finally the conclusion. I mean, the picture you have in your conclusion. But somehow, okay, in their calculation, they arrive at a cross-section which is exponentially small and which should be compensated by an entropy factor. And our reinterpretation of your result is that the tree-level cross-section is exponentially large instead of small, but the virtual corrections make it okay. And so, but in order to carry out the calculation consistently, we have to define well what this sigma n means. I mean, in a sense, they have to include what you were discussing an hour ago, for instance, emission of extra soft stuff below 1 over r. I don't know if, anyway, so I wanted just to mention this because it could be relevant for the previous topic. Okay, that was all I had to say. So we can open the discussion.